F, of course, and U for, this is electrical potential energy. The U is electrical potential energy, this is the force. This is the force acting on this charge Q when this charge Q is placed somewhere where the electric field is this. And because this is the electric field at that location, this cannot be the electric field generated by this charge. Because then you will be divided by 0. So I like to call this, it's external to this charge. In other words, this electric field is not the one produced by this charge. And it's the same thing over here. This is the electrical potential energy of this charge. When this charge is somewhere where the electric potential is this, which couldn't be the one generated by this one because then it's a field over 0, which it's also undefined. So this electric potential is external to that. So that's what those mean, right? So some problems we want to solve using energy arguments, and others you can use forces so that then you can get accelerations and so that you can get final velocities. But that's useful. You know, you can use the kinematic equations only when the acceleration is constant, which would be when the force acting on the particle is constant, which means the particle would have to be moving in a region of space where the electric field is constant. And so far, we've only talked about one case when the electric field is constant. Actually, 2 cases. Do you remember for which case there's an electric field over some region of space where the electric field is the same everywhere in that space?
Are they planes?
Yeah, so if you have like infinitely large sheets with charge, planes of charge, right? Then the electric field is, if you just have one sheet, then it's sigma over 2 epsilon naught. That doesn't have any dependence on position. Or between 2 of them, right? The other case, where the electric field is constant, but usually you don't consider a charged particle moving in there, is, well, what happens if the electric field is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0? Where else is electric field 0, 0, 0, 0, 0, 0, 0, 0?
Inside of a conductor.
Inside of a conductor. Except that inside of the conductor, you don't consider the charge moving, freely in there. But it's the same, it's constant. All right, so very important to understand what this is. This is discussed in chapters 21 and 22. This is discussed in chapter 21. Now this is discussed in chapter 23. So we're calculating this quantity in chapter 23 so that we can figure out what the electrical potential energy is, and then use, electrical potential energy. If it gets converted to kinetic energy, then we can figure out how fast the charge is moving somewhere else. One thing that I would like to, and I did an example last time, right? I mean, we had a fixed point charge. I think I said, I gave it a charge of 3 nanocoulombs plus 3 nanocoulombs, and then we found out what the electric potential would be at 3 different places, right? And then we said, what happens if I press another charge at one of those locations and I let go? Which way would it go? And if it goes in one particular direction, how fast would it be moving when it gets to that other location, right? So we kind of did that. What I would like to talk about now is what is the connection between this and this? And actually, there is a connection between this and this. But for now, let me talk about what is the connection between this and this. So for example, if I tell you there is a point charge here in space, let's say plus Q, right? Maybe a proton or the nucleus of an atom, or some point charge Q. And I ask you this question. At this point over here, some distance r away from it, what is the electric field over there?
KQ over I squared.
Correct. That's the magnitude. What about the direction? I mean, the electric field is a vector pattern, right? So which way would it be directed?
Outwards, like parallel to the radius.
So away from the charge, right? Because the charge is positive. Is there a charge over there? Not necessarily. All I've given you so far is this charge. This is just a point in space. That could be vacuum. Yes? So, but there is an electric field there. Let's call it something generated by this charge over there. And that something can be described in terms of a vector quantity with magnitude given by this direction away from the charge because the charge is positive. Now, if I ask you, what is the electric potential over there? At that same point, what is the electric potential? What would you say is the electric potential? KQ over R, correct. Now, what is the direction of that? There's no direction because electric potential is not a vector quantity, it's a scalar quantity. Now, suppose, that was simple, right? I gave you the point charge and I asked you what's the electric field. And then, given the point charge, what's the electric potential? Suppose I didn't know what was producing that electric field or that electric potential. Can I figure out what the electric potential is from this? Because maybe I know that. Can I get the electric potential from the electric field? Or vice versa? Could I be able to figure out what the electric field is if I know the electric potential? And you might think, well, just divide by R, right? But that's not correct. Because, well, I'll save that comment. What if I take this expression for the electric potential? So let me show you how to go from here to there. Let me take this expression, which is KQ over R, and I take the derivative of this V with respect to R. What is dV dR? What's the derivative of that with respect to R? Negative? Exactly. And what if I multiply that by minus 1? Then I'm going to get minus dV dr equals KQ over R squared. And that's actually this magnitude, right? So the way that they are really connected is through a derivative. It's not just dividing one thing by another one, but it's really a derivative. But this is really an operation, a mathematical operation that just goes beyond that. Because notice that I said, I want to go from this quantity to this quantity. This quantity here is a scalar, right? But this quantity here is a vector. So to obtain this vector, what I do is I do something to this scalar. And I'm taking a derivative with respect to something. So this scalar potential here is a function. It's a function of R. I'll tell you the distance R, and then you tell me what the electric potential is. So I'm doing something to this scalar function, and it gives me a vector. And usually in calculus 3, you learn about a mathematical operation where you differentiate a scalar function and you get a vector out of that. It's called it starts with G. There is a mathematical operation where you're given a scalar function and then you take a derivative of it and you end up with a vector function. What is that mathematical operation? You say you take the what of that scalar function? The who? The gradient. G starts with G. I said G. Good. It's called the gradient. So when you take calculus 3, which I think most of you are already taking it, but I don't know if you've learned about gradients, divergences, curls.
I took Calc 3 and I don't remember.
What's that?
I said I took Calc 3 and I don't remember curls or gradients.
No, but did you hear about them?
I think a little. We were a little behind. We didn't get through all the coursework.
So it's a mathematical operation where remember, when you take a vector and you multiply it by another vector, but you get a scalar quantity, what was that mathematical operation called? The dot product, right? or scalar product because the result is a scalar quantity. If you take a vector and you multiply it by another vector, but you get a third vector, what was that operation called?
Cross product.
The cross product, also the vector product, because the result is a vector. So, those were manipulations where you multiply two vectors. In one case, you multiply the two vectors and you get a scalar. That's called the dot product. In another case, you multiply the two vectors and you get another vector. That's called the cross product. In this case, what you're doing is you're multiplying, well, you're not multiplying. You're taking the derivative of a function that's a scalar, and you end up with a vector function. That's called taking the gradient of the scalar. So, and the symbol for the gradient, I mean, have you all heard about the gradient or no?
No,
No, you never heard about the gradient.
never,
Ever.
ever.
No.
Good. You first heard about it at OCC.
Yeah.
Okay. It's kind of a cute operation. I mean,
I'm scared.
you also learned.
I'm scared.
You also learned another one, right? In physics 185, you multiply a scalar quantity by a vector, not multiplying two vectors, but a scalar by a vector. What do you get?
A vector.
You get a vector. And we make a big deal. What can you tell me about the direction of that vector that you get? It's the same as the direction of the vector that you multiplied
It's positive.
if the scalar is positive, that you multiplied it by. But the vector that you get is going to point in the opposite direction to the vector that you multiply by the scalar if the scalar is negative. Right? So those are different operations. So the gradient is it's a mathematical operation where you take a derivative of a function, of a scalar function, and you end up with a vector function. It's called taking the gradient. Actually, what you use, so I'll just tell you this so that you feel good when your professors talk about it in math. So a little aside. Oh, I should write bigger. Right? A little aside. Right? So this triangle, which is, this is what? What is this? Delta. But if the triangle is upside down, it's not called delta. This is defined as the del operator. Or the del operator. Anyone heard that in Calculus 3? Yeah, the del operator. And there are expressions for that thing, for the del operator, in rectangular coordinate systems, in Cartesian coordinate systems, in cylindrical coordinate systems. So in Cartesian coordinates, let me do it here. Number one, in Cartesian coordinates, or rectangular coordinates, the del operator, this is, where the position of a particle is x, y, z, x-axis, y-axis, z-axis, right? So the del operator is defined as the derivative with respect to x, I hat, plus j hat times the derivative with respect to y, plus k hat times the derivative with respect to z. You know about partial derivatives, right?
Yes.
Yeah.
Yes.
Okay. So that's what the del operator is in Cartesian coordinates. Right? That's when you have, let's say this is x, this is y, this is z, and there's a point, right, and x, y, z. Or some books do this. They call that z, they call this x, and then they call this y. So, but it's the same, right? It's a matter of. So that's the definition of this thing called the del operator. In spherical coordinates, that's when you have r, theta, and phi to locate a point, right? So in that case, you have, and it's actually usually different in physics than in mathematics. But it's just a matter of calling names. So this is the x-axis, this is the y-axis, this is the z-axis. So I guess to be consistent with that, I'll say this is the Partition coordinates, right? Then a point over here in space, right? It's labeled by r, theta, and phi. R is the distance from the point to the origin. Theta is the angle with the z-axis. I think in your math books, they actually call that phi. And then if you project this point onto the xy plane, then this angle is phi. So this is called the polar angle, right? Because it's like this. And this is called the azimuthal angle. I think in your math textbook, calculus textbook, I think they call this phi and this one theta. It's backwards, I think.
Yeah, they call the one with the line through it horizontally theta, and then they call the one with the line through it vertically phi.
But in most physics books, we do it like this. So the del operator is, and I have to think about this because this is not something I memorized. What I remember is a picture, and then from the picture I get it. Notice, it's a derivative, this did the x, this is an increment in distance along the x-axis. This is an increment in distance along the y-axis, and this is an increment in distance along the z-axis. So, in spherical coordinates, there's an increment in distance along the r-axis, right? Or along the direction of r, in the direction that r increases. There's an increase in distance along theta. Actually, theta would be this way, and phi would be, in the direction of this phi. So it would be r hat, it's a unit vector in the radial direction, ddr plus, and then a unit vector in the direction that the polar angle increases, and the unit of length over here would be r d theta, so it would be d. And then for the other axis, it would be r sine theta and then d phi. So okay, so this is the del operator. Now, notice that, and then there's cylindrical coordinates, but I don't know if you want me to write this.
Can I add something that doesn't matter, but it's like kind of important? What is that Greek letter that's like a backwards 6? What is that called?
It means a partial derivative.
What's the name of it?
Delta.
Oh, it's delta. Okay.
I mean, I don't know if it's delta. Actually, delta is this.
I always thought that was rho.
But this is no. Rho is this.
Okay.
This is rho.
Okay.
So this is delta. This is the lowercase delta in Greek, and this is the uppercase delta in Greek. So that one, I don't know. I don't know what. It's a simple use for partial derivatives, but I don't know if it's actually a letter in Greek. I gotta ask my Greek friends. I think it's not a Greek letter, because what if they had to take a derivative with respect to a variable described by that? Then you would do like d, and then that wouldn't make sense.
Right.
It's like, well, 2 to 2. And you have them in cylindrical coordinates. Let me not, I can do it if you want me to. But, the reason why I wrote it like this is because of the following reason, right? the relationship between the electric field and the electric potential is actually this. That's the relationship between the electric field and the electric potential. When, you know, this is in electrostatics. Let me use this to get this result over here. Okay? So, if in this problem, I knew this. I knew the electric potential. So, this would be like this. E equals the negative of del, and then the electric potential is just K Q over R. K Q over R. Right? And because we had a charge over here at some point, we can think of that charge as being at the origin, and then all that matters was the distance. I mean, suppose Q is here. Does it matter if I go here where this R is the same? What would the value of the electric potential over there?
The same, since it's a
The same
scalar.
thing, right? K Q over R. All that matters is the distance to the charge. So it doesn't matter if it's, you know, X, Y, Z. It's all that matters is the distance to the charge. So in the most appropriate coordinate system to use for this particular problem of what is the electric field and its potential generated by a point charge are spherical coordinates. Notice that in spherical coordinates, this is what? E equals minus. Now, this del is this in that coordinate system. And this will be r hat ddr plus theta hat 1 over RT theta plus phi hat 1 over r sine theta dd phi. And then I have to apply this to this function, which is KQ over R. Now, is this function over here a function of theta? No. Does it depend on the polar angle theta? No. Does it depend on the azimuthal angle phi? No. So therefore, when this derivative here acts on that function, is going to give me 0. Because that's not a function of theta. There's no theta in there, right? And when this derivative acts on that, it's going to give me 0 also because this result here doesn't depend on phi. The only derivative that will matter is this one, because this is a derivative with respect to r, and this function is a function of r. So, what do you get if you do this? E equals minus r hat. That's just a unit vector in the radial direction. What is the derivative with respect to r of kq of r? Kq is a constant. So, what will that be? I'll write it out. ddr of kq over r. So what do you get? Minus r hat. Kq is a constant, right? And what is ddr of 1 over r? Negative 1 over r squared, correct. And then this negative and this negative gives me a plus. And then I have this result, that the electric field equals, it's a vector, and then I have r hat for the direction, which is positive r hat, so it's radially outwards. And then I have a magnitude of kq over r squared, which is precisely what we wrote down over here. We just memorized that result from chapter 21. That the electric field generated by a point charge is a vector that has a magnitude of kq over r squared, and it has a direction that points away from the charge if the charge is positive, towards the charge if the charge is negative. But I want to show you how this operation over here, this one, right? This is a differential operator called the del operator. When this operator acts on this scalar function, I end up with a vector. It's called taking the gradient of that scalar function. So the connection, because if I give you that the electric potential is kq of r, that's a scalar function. If I ask you, what is the electric field associated with that? So you gotta do something with that function that in the end gives you a vector. So how do you, and this particular manipulation here is you say that the relationship between the electric field and the electric potential, which is a scalar function, and the electric field is a vector function, right? Is you gotta take the gradient of the electric potential, but then if you just take the gradient without the minus sign, you get that the electric field points towards the positive charge, but that's not what we know of. So therefore you put in a minus sign to fix the direction. Yes?
You mean that if that one is negative charge, then you only have the
So good, I like that question. Suppose this charge is negative, right? Then this is still true, this is still true, except that this electric potential would be K, well, that Q is gonna be negative, right? And then that minus and this minus will make this a plus, it'll make this a plus, it'll make this a plus. Now you don't have that minus to cancel that, so the result is gonna be minus, which is in the minus r hat direction, which is towards the charge. So it still works. So anyway, that's called the del operator. I'm going to erase this. You're going to learn about this in Calculus 3, or you're supposed to, but it's very important stuff. Because, like the problem that you did today, for example, right? It didn't deal with a sphere, and it didn't deal with a point charge. It dealt with a cylinder, right? So then cylindrical coordinates is more appropriate to use in that case. But you didn't need that for today's quiz. So let me erase this. But let me at least tell you the following. So there is this del operator. It's just an expression. It's a differential operator because, you take derivatives. You use it, by taking derivatives, right? I mean, it's called a differential operator because in Cartesian coordinates, this is defined as I hat d dx plus j hat d dy plus k hat d dz, right? So notice, you take derivatives, right? So it's a differential because you take derivatives. Operator because this operates on something. It operates on something to give you something, right? So when this del operator acts on a scalar function, so del acts on a scalar function. So that's called taking the gradient. Let's say the scalar function V, like the electric potential, taking the gradient of the scalar function. So you just write it like this, del V. That's the gradient of the scalar function. But you could also have this del operator, this one, act on a vector function. Okay? Such as, let's say, should I call it E? It's a vector. Not necessarily electric field, but just any vector E. So in this case, this is called, so what you have is, but if this thing acts on a vector, notice that this thing itself has I hat, j hat, k hat. When it acts on a vector, it can act on a vector via a dot product or via a cross product. So when this acts on a vector function via the dot product, this thing is called taking, anyone know? Not the gradient. The divergence of the vector function. And it's written like this, del divergence, right, of E. It's a dot product. And the del operator could also act on a vector function, but not via the dot product, but via the cross product, right? So del acts on a vector function, let's say A, via the cross product. And that's called taking the curl. So that would be like the curl of the vector function. So if it acts on a scalar function, it's called the gradient. That's the gradient. Just del times the scalar function. No symbol, no dot, no cross. Just no symbol. If it acts on a vector function, it can actually act on a vector function in either of two ways, right? Via the dot product or the dot product. The dot product or the cross product. So the dot product, right? Then it's called the divergence. And you use the dot. This is the divergence of E. Now, you could also have del act on a vector function, but this time via the cross product. And now you use the cross here. And this is called taking the curl. So you will learn about gradients, divergences, and curls. Do you remember, like in chapter 1 of the textbook? You have a vector. You have a vector. Let's say vector A. Well, if you multiply it by a scalar, let's say, 3 times A, right? What do you get? You get a vector. You didn't write 3 dot A, you didn't write 3 cross A. It's just a scalar times a vector, right? If you multiply this vector A by another vector, well, then you say, can I multiply it via the dot product or the cross product? So you can say A dot B, that's the dot product, and that gives you a scalar, right? But you could also multiply that vector A with another vector via the cross product, like A cross B, and when you do that, you get a vector. And actually, that's what you're doing over here. This here this is like this. And the result is a vector, right? You take the gradient of the function and the result is a vector. Right? We took the gradient, we said the gradient of this, reverse the direction, and that gives us a vector. Take the gradient of the function, you get a vector. Taking the divergence of the vector function, right? That's like number 2 over here. The result is a scalar, right? When you do this, you get a scalar. But you could also take del, have it act on a vector via the cross product, that's the curl, but that one is like this. And this is a vector. So if you remember this, if you change this scalar to a del operator, del, you're going to get vector, scalar, vector. You're going to get essentially the same thing, except that with the del operator, instead of calling this just a scalar times a vector, you say the gradient. Instead of taking the dot product of the, just a vector with another vector, you take the dot product of the del operator with the vector, you get the divergence, which is a scalar function. And in this case, right, the del operator dot cross with a vector is going to give you a vector, and that's called the curl. So this is like a curl, this is like the divergence, and this is the gradient. So you learn about those in calculus 3, I think, is when you learn about those. Now, when you're learning it in math, it may be like, well, you know, we learn it, I'm gonna take a test and then I'm gonna forget about it. Well, electric fields in electromagnetism, electric fields are obtained by calculating the gradient of the electric potential function. And I wrote this like this because just like there is an electric potential associated with electric fields, right, linked to electric fields so that you can calculate electrical potential energy, when you talk about magnetic fields, there's something called the vector potential. You do something to that vector potential to get the magnetic field. And what you do to that vector potential is you take the curl of it. So in electromagnetism, you take the curls of a vector potential, you get a magnetic field. You take the divergence of an electric field and you get the electric potential. And you take the gradient of the electric potential and you get the electric field. So, you know, also in fluid mechanics, right? You talk about divergences, you know, in the heat equation in thermodynamics. If you have two of these del's together, like what happens if you take a del and you dot it with a del? Not a del the singly, but you know. What do you do? What do you get if you dot this with itself? I hat dotted with j hat is going to give you 0. I dot k is going to give you 0. J dot I is going to give you 0. J dot k is going to give you 0. K dot I is going to give you 0. K dot j is going to give you 0. But I hat dotted with I hat is. How much is I hat dotted with I hat? 1. What is j dot j? 1. And what is k dot k? 1. So the only when you I didn't like that look in your face. So if I say what is del dot del in, let's say, Partition coordinates, this would be I hat d dx plus j hat d dy plus k hat d dz. Dotted with this is the first del. This dot is this dot. And then this del is I hat d dx plus j hat d dy plus k hat d dz. Now you multiply it out. I dot I is 1. So therefore you're going to get the second derivative with respect to x. I dot j is 0. I dot k is 0. So j dot I is 0. But j dot j is 1. So that term survives. Now you get the second derivative with respect to y. And then k dot I is 0. K dot j is 0. But k dot k is 1. So this dotted with that is 1. So then you get the second derivative with respect to z. And so this is written as del squared. And what they do in mathematics, this is called, anyone know the name of this particular differential operator? Exactly, the Laplacian. That's what this is. And in, chapter 32 of this textbook talks about electromagnetic wave propagation. And there's an equation that describes these electromagnetic waves. Well, the equation is this. This is the equation for the electric fields, and this is the wave equation for the magnetic fields. Notice, it's the Laplacian of the electric field. It's the Laplacian of the magnetic field. This B stands for magnetic field. And this is the second derivative of E with respect to time. This is the second derivative of the magnetic field with respect to time. C is the speed of light in vacuum. This is the way you write down the wave equations, electromagnetic wave equations in vacuum, right? So they involve this Laplacian. What the hell is a Laplacian? It's del squared. What the hell is del squared? It's del dotted with itself. But what is del? It's a differential operator which takes various forms in different coordinate systems. What I'm saying is that this language of mathematics that you will soon learn if you haven't learned it or been exposed to in Calculus 3, right, comes up again, or very soon it's going to come up again, especially when you take, I suspect most of you are engineering majors, and so you're going to, this is going to come up again. So normally, in this course, since people are just taking Calculus 3, most of you, and you haven't been exposed to the del operator, right? You just say, probably my notes, that's what it just says, right? Oh, the electric field, you just see something like this. It's minus, in fact, I'll write it like this, minus dV dr. You might just see it like that. But this is really a vector. So, gee, what's up? Right? So it should really be like this. Well, I should do this. But this is only true if the electric potential only depends on R. What if it depends on theta? What if it depends on phi? Then you gotta use the entire enchilada over there, and this is really minus the gradient of the electric potential. So this is more general. So in physics 280, you just are introduced to it like this, right? I said you have a point charge plus Q over here at a distance r away. The electric potential is KQ over R. And the electric field is KQ over R squared with a direction associated with that electric field. And you might just think that the relationship between these two quantities is, well, just divide this by R and you get that. But first of all, you can, if you just divide that by R, how do you make this a vector out of just dividing something with a variable? So the real connection is through this gradient, right? The gradient of the electric potential function will give you rise to the electric field vector. And that's a language that you will soon be introduced to in your math courses. And sometimes when you begin to learn about these topics in math, it's like, well, you know, I'm not a math major, so I don't care. Or just learn it so I can do one of the tests and then I'll forget about it. But it comes back, and it comes back, and it comes back, and so on. So I don't mean to scare you, I need to get you excited and motivated so that, hey, I've heard about that thing. So, something else. So look what I did over here, right? I mean, let's see. So I kind of go around this gradient, you know, by making comments here and there, right? Oh no, that was a good point. I did write it in there. And I did write it in there. Okay, I feel good about it now. But you don't have to know this. Oh my goodness, son of a gun. That's good. Okay, that's just extra stuff. I mean, you're not OCC. You get introduced to the stuff right here. So, but let me just use physics to say something about this guy over here, right? So, the question is going to be this. If I know the electric potential somewhere, how do I get the electric field? Well, you take a derivative and you multiply by minus sign. Piece of cake. What about the other way around? What if I know the electric field and I want to get the electric potential? Then what's the reverse operation of taking a derivative? It's integrating, right? So the way that I wrote it in my notes over there, and this I want you to learn. So, since you can think of the electric field like minus dV dr, right? It's really like this, right? So if I want to solve for the electric potential, I can write it like this. It's actually minus E. So that minus sign is this minus, and then I want E multiplied by the R. But it's through a dot product. So that's what I have over here. In general, like an infinitesimal displacement ds, It could be along the x-axis, along the y-axis, along the z-axis, along the radial axis. Just some, like an arc length type of thing. So this is what we begin with. All right? So, what if I integrate both sides of this equation? What if I integrate it? Let me get rid of this here. What if I integrate this equation by putting integral signs on both sides, right? So, the integral on the left-hand side is with respect to what?
E.
V, potential, right? So my limits of integrations must be what? Values of electric potential. Suppose I integrate from VA, like the potential at some point A, or V1 to the potential at some point B. Now, the integral on the right-hand side is with respect to what variable? R. So I integrate from R equals, well, I gotta match that limit with this limit. So if this was at position A, let's say this is from radius A to radius B. And what is the left-hand side of this equation? I mean, I can, even without telling you anything about the problem, right? I cannot solve the right-hand side of this unless I tell you something specific about this electric field. But I can do this integral, right? We don't need to be talking about a specific case for me to do this integral. What is the integral of the V? V. And I evaluate it from VA to VB. And then I get this other thing over here. So this is what? VB, I'll do it here. VB minus VA equals minus the integral of E dot dr or ds?
dr.
Either one. Right. And this would be from R equals A to R equals B. Now, without talking specifically about a particular problem, let me ask you this question. One, what if over some region of space the electric field is zero? What if that's the case? What if this is zero? What will VA be? What will VB minus BA be equal to? What? If this is zero, this whole thing is going to be zero. And this means what? That the potential at position B is the same as the potential at position A. In other words, this is uniform, right? Or constant. Do you know, I asked this question earlier today, of a case when the electric field is zero in some region of space? What did you say?
Conductor
Inside a conductor. So inside a conductor in electrostatic equilibrium with that condition, right? Inside a conductor with electrostatic equilibrium, just a conductor that you charge and then you left it alone, right? Didn't connect it to anything else, just left the charge in there. Then that charge, we said, is going to go to the surface or surfaces of the conductor. It has more than one surface, right? And we did problems like that with more than one surface and another charge nearby. So if you have a conductor in electrostatic equilibrium, then if it has a charge, the charge of that conductor is going to go to the surface or to the surfaces. And the result of that is that it's going to make the electric field inside the conductor equal to zero. And since inside the conductor, inside the body of the conductor, the electric field is 0, what can I conclude about the electric potential inside that conductor? It's going to be constant. Not necessarily, it could be 0, 0, 0, 0, 0, 0, but it could be 2 volts, 2 volts, 2 volts, 2 volts, 2 volts, 2 volts. Or it could be minus 5 volts, minus 5 volts, minus 5 volts, minus 5. It's going to be constant throughout. Yes? Now, what happens if over some region of space there is an electric field? Right? Then there are a few possibilities. There's a dot product and there's a minus sign that I like to address. So that's another question. Can I erase this now? Essentially, it means the following. Suppose there's an electric field here, like this. In some region of space, maybe there's a lot of positive charges over here, right? And they generate an electric field that way. Or maybe there are a lot of negative charges here which generate an electric field towards it. Right? Whatever, I'm not interested in what's producing that electric field. Suppose there is an electric field in this region of space. Right? And suppose the electric potential here at this point is 10 volts. And I ask you, maybe in this region the electric field is like this, right? Suppose I ask you, what is the electric potential here? I went deliberately perpendicularly to the electric field line. So it's like my dr, or maybe it's better to write it as ds. It's like my ds is perpendicular to the electric field, but I have a dot product over here. What happens if the electric field is perpendicular to that ds? What is that dot product going to be?
0.
0. And if this is 0, then the potentials at the 2 points are going to be the same. So therefore the potential here, if that's 10 volts, is going to be 10 volts here too. So if you move perpendicularly to an electric field, the electric potential is not going to change. It's going to have the same value as, well, it's just whatever it is, it will be that value. Now, what happens if I consider, it's like I'm over here, I'm going to draw myself, suppose that's me, and the electric potential there is some value, like 10 volts. Suppose I walk in this direction. If I walk to new locations, and I walk in the same direction as the electric field, the meaning of this minus sign is that the electric potential is going to get smaller. Right? Because it's like, if this is in the same direction as that, then this dot product is going to be positive, and this minus sign is going to decrease whatever this is. So the electric potential is going to get smaller. So moving in the same direction as the electric field decreases the electric potential. Well, if you move in the same direction as the electric field, and as you go to those new locations, the electric potential gets smaller, and if you move perpendicularly to the electric field and the electric potential doesn't change, what do you think happens if you were to move in the opposite direction to the electric field? This is you going this way, or you going this way, to new locations. It's going to get bigger. Right? So here, this increases B. So the physics that you should remember from this formula is the following. What's the meaning of the minus sign? The meaning is that if over some region of space there is an electric field, right, the potential somewhere is going to be so many volts. But if you go to new locations and you get there by walking in the same direction as the electric field, the electric potential is going to get smaller. If you walk to new locations where you walk in the opposite direction to the electric field, the electric potential is going to get bigger. And if you walk perpendicularly to the electric field, the electric potential is not going to get smaller, it's not going to get bigger. It'll stay the same. It's constant. Right? And that one stayed the same is also connected with this, with the dot product. That's the physics behind that. In fact, remember the example that we did of the point charge plus Q being 3 nanocoulombs? And we calculated the electric potential 1 meter away? What was the electric potential over there? What did we calculate? What was that? 27 divided by 1, so that was 27 volts, right? And then 2 meters away, what was the potential over there? Was it
18 volts.
13.5? And if you go 3 meters away, what was the electric potential there? 9 volts, right? Well, over this region of space, what is the direction of the electric field generated by this charge? Which way is it pointing? Notice the charge is positive. So electric field points this way. I don't like this red. Well, suppose I'm here. Right? If I'm 2 meters away from that charge, the electric potential there is 13.5 volts. What if I walk in the same direction as the electric field and I get over here? What happened to the potential? Did it decrease or increase? That's what I'm saying over here. And what if I were to walk in the opposite direction to the electric field so that I go to this new location? Later on, I'm going to be 1 meter away from the charge. The electric potential there is getting bigger. Yes?
Professor, kind of a dumb question, but the electric field from that point is also the radius, right? It's not just like a straight line.
So at this point, I cannot tell you what the electric field is because that would be kq over 0 squared.
Right.
So that's undefined. But at any point, like if you ask me here, it's away from it. Over
Right.
here, it's away from it. Over here, it's away from it, right? It's away from it. So I'm just focusing on that line.
Oh.
Yeah. Always radially outwards, away from it. So positive, away from the charge. That's positive. If the charge is negative, the electric field points towards it. So let's do the following calculation where we use this one. And I like to start from scratch. So very important physics over here, right? The dot product means that if you move perpendicularly to the electric field, the electric potential is constant. It doesn't necessarily mean it's 0. The change in the potential is 0, which means it's constant. It could be 0, 0, 0, 0, 0, 0, 0, but it could be 1 volt, 1 volt, 1 volt, 1 volt, 1 volt, 1 volt, the same value, right? And the minus sign means that if you walk in the same direction as the electric field, the electric potential gets smaller. It decreases. Very important comments to remember. What if we have a set of parallel plates? Consider this problem. Two infinitely charged, no, infinitely large is what I meant to say. The charge, but infinitely large. And oppositely charged plates with sigma, with charge per unit length, I'll make it uniform, with uniform, not per unit length, charge per unit area, and separated by a distance d. So I have this infinitely large sheet plus sigma, and another one negatively charged at a distance d away. Okay, so I'm gonna do this. I'm gonna introduce like an XY coordinate system, and I'm gonna think of this as X, right? And if you like, let me use a different color for the coordinate system. Like I'm gonna call this the X-axis, and I'm gonna call this the Y-axis. So notice that the positively charged plate is here at the origin, and the other one is here. This one is at x equals d, and this one is at x equals 0. And we have vacuum in between. This plate on the left is at an electric potential V, what should we call it? I don't want to call it 0, because that may sound like initial. How about I call it V plus? It is the potential of the positively charged plate. And let's call this the potential of that plate V minus. So the question is this. Question, what is the potential difference between those two plates? And I'm going to define this as delta V. So what's this? In other words, and what is the difference of two potentials? What do we call that? The voltage, right? I'm asking, what's the voltage between these two plates? Or across the two plates? So how do I find out what the potential difference is, or what the voltage is between these two oppositely charged and very large plates? They have equal charge, except that one is positive, the other one is negative. So, what I do is this. I start with this expression here. In this case, it's dx. The distance increment from one to the other is ds, right? This means that I need to know the electric field. See, let me integrate this, right? So I do this, and I do that, right? Now, which of these two plates is at the higher potential? When I calculate this difference, will it be a positive number, or will it be a negative number? When I take the potential here, minus the potential there, will it be a positive answer, or will it be a negative answer? Or will it be 0? What do you think, and why?
Would it be 0 because they both have the same charge but opposite? Which would mean we add them together, so it's going to be 2 times the potential.
What's that?
2 times the potential.
I'm sorry.
That would be 2 times the potential. Electrical potential.
So will it be positive or will it be negative? Positive? Why positive? No, this is not a point charge. The K cube R doesn't apply. That's only for a point charge. This is charge distributed over an infinitely large sheet. So the K cube R and K cube R squared, they don't apply.
Subtracting the negative sigma adds to the positive sigma, no?
How do you know? So she said, because I'm going to get a positive answer because the potential here is bigger than that. Good. How do you know that that's the case? Yes?
The distance in x.
What's that?
The distance of the positive charge in x is the distance of the negative charge.
The distance from where? One is here, the other one is there. You make it sound like it's the distance, like this is closer to something, but closer to what? You have an idea? Or
Positively charged
since we're working on it.
No? Yes?
So the electric field would go from left to right, and you choose one point on x-axis, the potential on the right x-axis will be smaller than the one on the left.
Perfect. That's the answer. These charges generate an electric field in here pointing from where? From plus to minus, right? Electric field is away from the positive charge towards the positive charge. Suppose I'm here. If I go that way, I'm going to location where the potential is what? Smaller. And if I go this way, I'm going to location where the potential is bigger. So she said it right. The potential here is bigger than the potential there. But why was it bigger, right? So it's because there's an electric field, and also one of you said, I think they're the same. They can't be the same because there's an electric field between them. If there is an electric field, between these two positions, this is not going to be zero unless you go perpendicularly to the electric field. The only way to go perpendicular to this is to either go up or down. So when I calculate this quantity over here, I better get a positive answer, because the potential of the positive plate is bigger than the potential of the negative plate. How do I know that? Well, consider the electric field between those two plates. The electric field is away from the positive charge towards the negative charge. Well, if I move in the direction of the electric field, the potential gets smaller. So the potential here, if it's 3 volts, I know the potential here is going to be more than 3 volts. So when I take this minus that, I'm going to get a positive answer. If I ask the question, what is this? My answer has to come out negative, because I want this minus that, but this potential is smaller than that, so I'm going to get a negative answer. Yes? So notice, that's just from this minus sign that I was able to conclude that. Now let's work it out. So I'm going to say, okay, I want that potential difference. Notice that I want V plus minus V minus, right? So how about I put over here V plus and V minus? Regardless of what I have over there, this is going to be V plus minus V minus. And that's what I want to find out, right? So I just play with the limits of integration. I put in, this is on the left-hand side, this is an integral with respect to potential. On the right-hand side, this is an integral with respect to values of x. Right? I'm integrating with respect to x. But if I want V plus minus V minus, how about I put V plus upstairs and V minus downstairs, so that then I get this, which is what I was asked to find out, right? And then I just match them, right? I say, okay, this is minus. Now, this, so what is the value of x when the potential is V minus? What's the value of x at the location where the potential is V minus? D, right? Potential here. At that position, x is D. And what is the value of x at the location where the potential is V plus? 0, right? X is 0 at V plus, x is D at V minus. And then this electric field has to be the electric field between these two values. So what I care about is the electric field between this value of x and this value of x. And that's in between them, which is something not 0. So those two, yes? So those two, the potential difference cannot be 0. The only way for the potential difference to be 0 is if this electric field is 0. And if this is plus and that's minus, well, first of all, how are you going to get electric field 0 over here? That means you don't have them charged. So the potential is the same. Now, would you be okay if I get rid of this minus sign by doing this? And then switching the limits of integrations? You know the rule, right? The integral from a to b, f of x dx, with a minus sign, right? Is you get rid of the minus sign, and then you switch the limits of integration. So I don't like that minus sign, I'm going to get rid of it. So then I switch the limits of integration, right? Yes? Yes? Now, what do I know about the electric field in this region of space between two oppositely charged sheets? Now you should know this because you were studying for today's quiz, right? What do you know about that electric field besides pointing from plus to minus? Do you know the magnitude of it? What's the magnitude? Right? Which means it doesn't depend on x. It's uniform. Therefore, because it doesn't depend on x, I can take it outside. Piece of cake. So this is my delta V over here. And that's E times the integral from 0 to d of dx. And what is the integral of dx from 0 to d? With the understanding that the positively charged plate is at a higher potential than the negatively charged plate. This is an expression that many students in biology memorize when they take before they take the MCAT exam, which is an entrance exam to medical school. They call it VED. What many of them forget is that this is only true. I can get this result only if I'm able to slide that electric field outside the integrand. And I can do that only if the electric field is uniform. If it isn't uniform, I can't do it. And in an old MCAT exam, a former student of mine came to me and told me that they had this question. And it's one of those questions that you can answer in 2 seconds. So the question in this medical school aptitude test entrance exam was this. There's an electric field like this over some region of space. I'll make it simple. 10 volts per meter. And uniform. And that's 0, that's 1 meter, that's 2 meters, that's 3 meters, minus 1 meter, minus 2 meters. And I'm cut the exam, right? And let's say that you're told that the electric potential over here is 200 volts. 2 seconds. Maybe 1. What's the electric potential over here? Ooh, that took more than 2 seconds.
Negative 2.
How much? 220. So, here's the way to do it. Quickly. And then you can be a medical doctor, I guess. Well, of course, there's a lot more than that. See, this only applies if the electric field is uniform, which is this, right? This is uniform. You were told that it was uniform. So, this means, right? This means the following. Delta V equals ED, right? So therefore I can say that E is delta V over D. And since this is 10 volts per meter, what this is saying that, notice, you have new units of electric field, right? What was the unit of electric fields that you've been using? Newtons per coulombs, because you were thinking of F equals QE, right? And if you saw for E, it's a force over a charge. And the unit of force is the Newton, and the unit of charge is the coulombs. So up until now, you know, the electric field is so many Newtons per coulombs, Newtons per coulombs. From this expression, you could also see that another unit that's just as good as Newtons per coulombs in the metric system is volts per meter. And what this means is the following. Because this electric field is uniform, what this value of 10 volts per meter, what this means, right, the 10 volts per meter, one way to think about it is this, is that if the electric field is 10 volts per meter, it means that if you walk 1 meter, either in the same or opposite direction of the electric field, the electric potential is going to change by 10 volts. It is not going to be 10 volts. It's going to change by 10 volts. So if I'm here, that's what we were given in the problem, right? If I'm here, the potential there I was told is 200 volts. And I wanted the potential over here. So I gotta walk this way, right? If I walk that way, I'm going in the opposite direction to the electric field. So is the potential getting bigger or smaller? And for every meter that I walk is going to change by 10 volts. So if this is 200 volts, this is 210, that's 220. Right? So this would be 200 volts. That would be 210 volts. This would be 220 volts. This would be 230 volts. This would be 190 volts because you're going now in the same direction as the electric field, so the potential gets smaller. Notice how important that, that concept is, right? I mean, 180 volts. You don't really have to do you don't even have to plug numbers into that. Well, if you plug numbers, you might get 180, right? But as opposed to the 220. But notice, if you go in the opposite direction of the electric field, the electric potential gets bigger. Are you ready for another one? For your honor? Okay. So, I'm going to change this, and I'm going to change that. I'm going to change that. Okay, so let's say the electric field is 20 volts per meter, and the potential here is 140 volts. What's the electric potential over here? 1, 2, 3, 4. How much?
220. 220.
Did I hear 220?
Yeah.
220? If I'm going that way,
Oh.
I'm going in the same direction as the electric field. What's happening to the electric potential?
60.
It's gonna go down. And for every meter that I walk, it's gonna go down by 20. So 140, 120, 100, 80, 60. It actually takes less time to say, 120, 100. When you write it down, you waste a couple of seconds, right? So it's important to know if you're going towards, in the same direction as electric field or in the opposite direction as electric field. This one should take you less than a second. Son of a gun, look at that. What is the electric potential here?
80.
Ooh, that was good. Because if it's 80 there and I go perpendicular to the electric field, it's not going to change. It'll stay at 80. Yes? Okay. But, you got an integral, you got a minus sign, an blah, blah, blah. What is the relationship between this baby here and this one? Through a gradient. It's just that we kind of camouflage it a little bit, right? And we just don't use the word gradient, I guess, in physics 280, but I guess here we do. How much time do we have? Nothing, I think, or what?
Like 13 minutes?
Okay, so I'll give you this other one. Let's make it more interesting. Or maybe, I don't know. And I hope you realize how many more things you need to connect, right? Like, okay, if I go this way, the increases goes that way. If it increases and it's perpendicular, then it doesn't change. But then, if the charge is positive, it feels away. If it's negative, it's towards it, right? There are a lot of details, little details, but they're fundamental. All those fundamental. So if you're going to review something, review those fundamental details have a problem like this. Let's make it a little bit more interesting. We have a dielectric sphere. Oh, I'll just say dielectric sphere. Radius A, right? Uniformly charged, so this is uniform. The charge per the volume, right? And there is an electric potential at the center. Let's call it V sub 0, like 0 distance from the center, like at the origin. And there is a potential on the surface. Let's call it V at radius A. Okay. So question, what is that potential difference equal to? Yes. So then you say, okay, I know this formula, right? I know this dV equals minus ETR in this case. I'm gonna do this, I'm gonna do that. If I want this difference, which potential do I put in the upper limit of integration over here?
VA.
When I do this over here, I want it to look like that. So what should be the upper limit here?
It's 0.
V sub 0, and this is V sub A, right? So therefore this is R sub 0, and this is R at A, right? I just match the limits, right? And then I don't like that minus sign, so right away I'm gonna do this. So this has to be the electric field where in space? Do I want the electric field out here? Am I interested in that electric field? Where should this electric field be that I need to calculate the potential difference between the electric potential at the center and the electric potential on the surface? It's gotta be between these two limits. So what I need to know is the electric field somewhere inside this dielectric, right? Yes? Right? This is the electric field be integrated from R equals 0 to R equals A. So when I need to integrate, I need to know the electric field right here at some distance R. What is that electric field right there? That's the one that goes in here. And then you say, how do I find the electric field over there? Ooh, chapter 22, right? I'm given a sphere, it's uniformly charged, so I'm gonna think of a Gaussian surface. So it's gonna be spherical, right? So that's my Gaussian surface, right? So then it's E times the area of my Gaussian surface of radius R, so E times 4 pi R squared, equals the total charge inside the Gaussian surface. Well, since this is uniform, it'll be the charge per the volume times that volume, which is 4/3 pi R cubed. Then you do the math, boom, 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 and you get E equals rho R over 3 epsilon naught. Okay, this is the baby that I need here. So this becomes from 0 to A, and that's rho R over 3 epsilon naught dr. These are constants, so I can take those outside. Rho over 3 epsilon naught r dr from 0 to A. Not difficult. What is that? R squared over 2 from 0 to A. So what's the answer? That V naught minus VA equals rho A squared over 6 epsilon naught. Like it? No? You don't like it? I don't know. I think that's exciting. You get to integrate, for heaven's sake.
That's you're assuming the sphere is hollow, right?
No, it's a solid one.
Oh, solid?
It's a solid sphere. There's charge all over the place. But, you know, if this were hollow, then I have an inner radius and an outer radius. I only have one radius, A. So the charge is all over the place. And I need to integrate, because I want the potential difference between the surface and the center, I need the electric field between those two. And so somewhere in there. But how do I find the electric field inside this solid dielectric sphere? Chapter 22. I learned Gauss's law, so I use that to get the electric field. Now that I know the electric field, which is a function of R, right, I plug it in there and I do the integral. Yes? Huh?
Yes.
In this case, well, the electric field is given by this. If rho is positive, R is always positive, this is positive, so the electric field is positive, right? So it points away, radially upwards. So the electric field points from the, well, here it's 0, and then it gets bigger, 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 bigger. So the electric field is bigger over there. So this is, remember we did a graph of that, I think? The graph of the electric field was like this. This is E, and it grows linearly with R, and then it goes like this, right? So the greatest value of the electric field, in this case, it's the greatest value of the electric field is on the surface, right? But the electric field points radially outwards. If the charge is positive. So going radially outwards, the electric potential at the center must be bigger than the potential at the, and that's why I put it in this order. So the answer comes out positive, as you can see from there, if rho is positive. Yes. So you will do homework problems where you have, what if you have a problem like this? Maybe it's hollow, right? You have a sphere, radius A, that's hollow, or inner radius A, outer radius B. Maybe there's rho in here, and there's vacuum in there. And I don't know, maybe there's another shell over here of radius C. Right? So this is vacuum. This is dielectric. And this is vacuum. This is just a shell with, let's say, minus Q. Thin shell. So suppose the potential here is Vc, and the potential at the center is V0. And I want to know what's the potential difference between V0 and Vc. What's the potential difference between here and here? And let me show you how you would do it. Just real quickly. The setup is it's the same setup. So I would say dV equals minus EdR in this case, right? And then I want the potential. Where did I want it first? It doesn't matter what the order is, right? So I said V0 minus Vc. So I put V0, Vc. This would be R equals 0, and this would be R equals C. That way, on the left-hand side, I'm going to get V0 minus V sub C equals, and then I have that, right? Let me change the sign of that, and then make it from 0 to C. This is R, right? EdR. So where do I want the electric field? Well, everywhere between the origin and the surface of the outer thing, right? So, for that problem, notice that this is vacuum, there's no charge in there. We could put a point charge in there if we wanted to. But because there's no charge in there, what is the electric field in this region?
0.
0, because if I do a Gaussian surface, there isn't going to be any charge enclosed. So electric field is 0. Right?
Mm-hmm.
Now, so in this region from 0 to A, the electric field is 0. The electric field inside the dielectric material is going to be something from B to C. And from A to B. And from B to C, the electric field is going to be something different. So you can call this E1, which is 0, this one E2, and this one E3. Right? Electric field here, there, and there, and then I get to the surface. But there are 3 different electric fields. So I cannot integrate directly from 0 to C. Because I have 3 different electric field expressions, actually 0 in here, then I just split up this integral. This will be the integral from 0 to A, with the electric field between 0 and A, right? I think I called it the E1. And then the integral from A to B, that would be E2, plus the integral between B and C. And the electric field between 0 and A, because there was no charge at the center, that electric field is 0, so then this guy is 0. And then I can figure out the electric field somewhere between points A and B. That's just Gauss's law applied to a sphere, different from the cylinder. It's really the same as the cylinder that we did today in the quiz, except that that was a cylinder, this is a sphere. And then I need to know the electric field outside of it. I need to know the electric field here, and I need to know the electric field there. And then I just take those expressions, right, that I obtain using Gauss's law, I put them here, and then I do the integral. So I hope you can see how the various chapters get connected with one another. If I want to do calculations of electric potentials and voltages, and I choose to integrate an electric field, then I need to calculate the electric field. But if I know Gauss's law, that could be useful in many problems. I mean, that's how you would set it up, right? I mean, you learned in math things like this, that if you have a function, and you integrate it from, let's say, A to C, and this is B, right? The integral from A to C of f of x dx, you can break it up into the integral from A to B of f of x dx. That would be, this function here, plus the integral from B to C of f of x dx, right? And that would be this other integral. So that's what I'm doing here. I'm going from 0 to C. So I'm integrating from the center of this problem, right, to this surface. But the electric field has different expressions. The electric field here is 0. Here is going to be something, which I don't know what it is because I don't memorize this expression, but it's going to be something. And the electric field here is going to be something different. So if I draw a Gaussian surface over here, the charge enclosed is going to be the charge in all of this. If I want the electric field here, then I draw a Gaussian surface there, and it's going to depend on the total charge only in there. So I get 0 electric field here, an electric field here that's different from the electric field over there. So I integrate from 0 to A, and then another integral from A to B, and then another integral from B to C. And whatever I get, that's it.
Wouldn't E3, since it's from B to C, wouldn't it just be 0, since it's also in?
No, because if I draw if I want to know the electric field here, right, and I draw my Gaussian surface, there is charge enclosed.
Oh, okay.
I'm not gonna get 0 electric field.
Okay, I was thinking because it's in the integral from since B to C, since it's outside of the dielectric sphere.
No, but
0.
outside is, no.
Okay.
I mean, if you, suppose you have this. So we have this. It's a hollow, this vacuum here. And then we have this. And this is a dielectric of radius B, and the charge per volume is rho. And I want to know the electric field there. And this is R away. This is Gauss's law, right?
Yeah.
So you just go like this. So, or radius R. So this is the electric field there times that Gaussian surface area. And then I want the total charge inside of that, which is going to be this charge. And that will be the charge per unit volume times that volume, which is the difference of the volumes of the two spheres. And when I solve for R, when I solve for the electric field, the 4 pi's and the 4 pi's and the 4 pi's cancel, so E equals rho over 3 epsilon naught, there's a b cubed minus a cubed over r squared. This is the electric field outside, which I called over there E3. And that one will go here. Then I integrate that from B to C. So, no, not, electric field is at 0 outside. Now, if I ask you, what is the electric field here? Well, if I draw my Gaussian surface, it will be E times 4 pi r squared equals, well, what's the total charge inside of this? Nothing, because that was hollow. So then that was the E1. That's 0. So that's this guy here. So to do these problems, you must know Gauss's law. Because if you calculate the wrong electric field, the answer is going to be wrong in the end. Okay, I'll stop here.
That wasn't my question.